when it comes to electricity, there's probably two main terms that you've heard about. The first one is current, and the definition of current is the rate of flow of charge. Now, this mean exactly? So let's say you have a circuit and you have a bulb with a back connected to a battery, and the battery is going to emit electrons in this case. But sometimes in overall it can pretty much be any charge, but more often than not it will be the electron, and they get emitted from the negative terminal of the battery. So the electrons go around the circuit, and what current is basically the number of electrons passing a point every second. That's what rate of flow of charge means. The amount of charge passing a point in a given amount of time. So by that definition, the fundamental current equation is given by I, the current, is equal to Q, which represents a charge, over time. You measure current using an ammeter uh, with this circuit symbol A. An ammeter which measures the current is always connected in series. We're going to go into another video into series and parallel in a bit more detail. Just take it for granted for now what that means. Ammeters are always connected in series. If you look at some units for this equation here, current is given in something called amps, or you can call it A, as like the unit letter. Charge is denoted by coulombs, which is this capital C, and time is in seconds. Now, the other big electricity term that you've probably come across is voltage. Voltage, or it might also be referred to, it can also be called potential difference, is the work done per unit charge. And you can kind of understand by this kind of equation that the equation for voltage which is denoted by the letter V, is equal to the work done, which I'm going to call it as WD, over Q, where WD is the work done or energy transferred in joules, Q is charge in coulombs, and V is the voltage or potential difference, and that's measured in volts, denoted by this V. Now, we saw earlier that we used an ammeter to measure current. So we have another circuit. In order to measure the voltage in a circuit, we use a voltmeter, which is circuit symbol V here, and it's always connected in parallel. We'll go through again why it's connected in parallel and this sort of stuff in our series in parallels video, which you should definitely go and watch. But for now, just take it for granted. I want to talk to you now about a notion called resistance. Now, all the circuit components that you're going to come across in AS level, all of them will have some form of resistance, unless they're a battery or a wire or an ammeter. They will all have some form of resistance. So what exactly is resistance? So let's say we have this wire or a resistor or anything. So in this case, let's say we'll have a wire, and usually wires don't have any resistance, but that's when we take it into an ideal case. Obviously everything has some form of resistance, but in this case, and usually when you're doing your circuit problems, you don't really consider the resistance of a wire, but we're going to look at the real life scenario where wires do have resistance. And in the wire, a wire is usually metal. You might know that metals consist of something called metal ions or positive ions, and these exist within the wire or in the resistor, whatever you want it to be. And also in the metal are delocalized electrons. And remember when we looked at the circuit, we saw that electrons were the charge that would basically carry the current through the circuit. So you have electrons going in here, flowing through. And what happens is when these electrons pass through, they will collide with these positive ions. They'll bounce off and collide with the positive ions. When they do this, the positive ions provide some sort of resistive force to the flow of electrons. They're providing a force against the way that the electrons are flowing. And that's what resistance is. Resistance is the resistive force provided to flowing electrons or charge by the positive ions. So I'm now going to go through some factors that might affect resistance. So let's look at temperature first. Temperature. So if we increase the temperature, you know that when a metal gets hotter or particles get hotter, they vibrate more. So in this case, the positive ions vibrate more. Therefore, there will be more collisions. And that makes sense if you think about it. The positive ions are vibrating more. It gives it a higher chance for the electrons to come and hit the positive ions. And that means that when the temperature increases, so does the resistance. As temperature increases, resistance, denoted by this capital R, increases. Now let's look at how current is affected by resistance. Now the more positive ions you have, the higher the resistance is. So the more positive ions, you have greater resistance. And what that means is you're going to get more collisions between electrons and the positive ions. And that means that the speed at which the electrons move through the wire or the component decreases. So the current will also decrease because the electrons move through the wire slower. So as the resistance increases, current decreases. Also, if there are more positive ions, you know the resistance increases. So resistance increases with more positive ions. It means that the energy needed for an electron or whatever to go through this resistance is greater. So you need more energy required. In that way, the voltage increases. So as resistance increases, the voltage required to maintain the same current or the same amount of flow of charge is greater. And with this relationship between resistance and voltage and resistance and current, we can form the famous Ohm's law equation, V equals IR, where V is voltage measured in volts, I is the current in amps, and R is the resistance measured in ohms, and it has that symbol. At a constant temperature, we know resistance stays constant. So therefore we can say that at constant temperature, the voltage is directly proportional to the current. So if you had a voltage versus current graph, you get a straight line, and the gradient is equal to the resistance. And be careful, sometimes in the exams, they might give a graph that's the opposite way around. In this case, the gradient is equal to 1 over the resistance. The final thing I want to go through in this video is power. Power is the rate of transfer of energy. And by that definition, the power equation is equal to energy or work done over time. And the unit for power is watts, given denoted by this capital W. Now there are three equations that you need to know for power. The main one is P equals IV, and the other two can be formulated by substituting in V equals IR into this equation. So if you were to say V is equal to IR and then sub in for V, we would get P is equal to I times IR, which is therefore I squared R. And if you were to rearrange and sub it in for I, you'd get P is equal to V squared over R. So those are your four power equations. And you can choose which of the last three to use based on what the question gives you. Sometimes the question might give you the current and the resistance, and you have to work out the power going through a certain component. In that sense, it'll be ideal to probably use the third equation, P equals I squared R. I advise you to go look at some practice questions in order to help reinforce what you've learned today. It's a good way to understand how to apply the content and the equations. Please make sure to subscribe, like, and comment, and feel free to watch any of my other videos if that will help you with your physics course, and good luck for your future.